Welcome PCS members and friends to our today's second seminar of the day. It is a pleasure to have with us Dr. Ryo Hanai, and I would like to invite our scientific host, Sergey, to introduce our speaker. Please, Sergey.
Yeah, welcome again to everyone, and it's a pleasure to have Ryo Hanai with us today. Let me say a few words about his scientific career. Ryo did mainly his entire physics education at the Keio University in Yokohama in Japan, and he finished that in 2016 with his PhD. And then he moved to Chicago to the University of Chicago, where he was a JSPS fellow, Japanese Society for the Promotion of Science, if I remember correctly. And he was working there for 3 or 4 years together with Peter Littlewood. Then he moved for a quite short time. Well, no, actually for more than a year, he moved from the physics department at the University of Chicago at the James Franck Institute. He moved to the Pritzker School of Molecular Engineering at the same university and became a postdoctoral scholar there until April this year, when he joined the APCDP, the Asia Pacific Center for Theoretical Physics in Pohang, as a junior research group leader with a focus on non-equilibrium many-body physics. And he will today speak about non-reciprocal phase transitions, which is, I think, a very interesting result and topic and paper, or maybe several papers, which he published together with Peter Littlewood and other colleagues recently. So, Ryo, the floor is yours. Please tell us more about non-reciprocal phase transitions.
Thank you, Sergey, for a very, very kind introduction, and thank you for inviting me to this, for giving a talk on this topic. So today I would like to talk about what we started to calling, what we decided to call non-reciprocal phase transitions, which is a new type of phase transition to our knowledge that strictly cannot occur in equilibrium. And I'll tell you what I mean by strict. So it's a collaboration, It's a collaboration mainly with Peter Littlewood at University of Chicago, and for the quantum-driven system projects, I was collaborating with Alexander Edelman, who is a student of the Peter Littlewood, and also Yoji Ohashi from Keio University, Japan. And I've also started talking to Vincenzo Vitoli and Michel Fouhard, who's working on active matter systems, and which we nicely had a great collaboration, which led to this results that I'm going to talk about today. So, so the outline of my talk is as follows. So I'll start with a general theory where I would like to generalize the the celebrated Landau-Ginzburg theory to be applicable to non-equilibrium systems, and try to convince you that there is a new type of phase transition that cannot occur in equilibrium. And I will give you several examples that of some systems that does that, which is a delivered quantum matter, namely a pluridon condensate, and some associated anomalous critical phenomena that would happen there. And also I would like to talk a little bit about the active matter result that we have. So let me start with the general theory. So needless to say, phase transitions are ubiquitous in nature. Not only these equilibrium transitions that you learn in textbooks, there are many non-equilibrium transitions as well, which includes laser threshold transition, synchronization. For example, this is a picture of a synchronization of fireflies, and also flocking can be considered as a phase transition for theorists, I mean, for physicists at least. Okay, so how do we understand equivalent phase transitions? Well, there is the equivalent phase transition is really nicely can be understood from the Landau theory. So probably this is needless for you to say, but the Landau free, I mean, what you do in the Landau theory is to first write down a Landau free energy, which you respect the symmetry of the system, and then the parameter that changes the minimum from some value to another value is the critical point. Although this approach is very, very simple, very nice thing is that you can predict the existence of, for example, the jump of the specific heat or the divergence of the stability for the second order phase transitions. Of course, the critical exponents of these are not fully captured by this Landau free energy because this is just a mean field theory. If you add spatial gradients and thermal noise to this, that obeys the fluctuation-dissipation theorem, you can systematically study the static and dynamical critical phenomena as done in Hovenberg and Halperin. So how about non-equivalent phase transition, and how should we understand these? Well, and in particular, does the Landau theory work for these kind of systems? One might argue that Landau theory is useless for non-equivalent phase transitions because there's no such thing as free energy in non-equivalent systems. But let me argue here that even in non-equilibrium, Landau theory does work in most of the cases to some extent. So let me take the directed percolation as an example, which is one of the most important class of non-equivalent phase transitions that is known. So what does the directed percolation ask is you take a chunk of a network like this, which consists of open and closed channel. This solid line represents the channel that is open, and that dotted line represents the closed channels. And it is whether the channel is open or closed is randomly selected with the probability P, which is a given parameter. And you ask, what happens if you try to pour a water from the top? And if you pour the water from the top, of course, the water will spread out. But we ask whether does the water spread all the way through, or does it going to stop at some point? It turns out that this is, it depends on what the P is. If you're smaller than some value of P, then it turns out that there will be always a finite penetration depth. On the other hand, if it's beyond some critical point, which is called the percolation threshold, the water will start to spread out all the way through. And at the critical point, this penetration depth that were finite diverges. And so the length scale diverges and also the time scale diverges as well, which is very close to what you see in the critical phenomena. I mean, continuous phase, in the continuous phase transition.
May I ask a question? What's the difference to so directed percolation? Well, what's the difference to normal percolation, so to say? Or
the directed percolation is it's a rule that the water can only go down and you cannot go up. While the percolation is somewhere that is a system that it can spread to the top as well. So there's no, in the usual percolation, there's no particular direction. While here, there's a direction that goes down.
And you say that this is of a principal difference, yeah?
Yes, yes. In terms of like the critical exponents, it turns out to be different. Yeah.
Thank you.
Right. So, right. Thanks. So how do we understand that why this phase transition happens. To understand this, let's divide decompose this to event by event. So as you see here, this channel here, the water just dies out, which means that one channel is lost. While here, there's an offspring event where the number of channel increase from 1 to 2. And there's another decreasing channel, which is a coalescent channel where the 2 channel coalesce to 1. So you lost 1 channel. So if you write down some mean field theory to this, you can, which is the density of the channels as a function of time, you can kind of phenomenologically write down these equation, which is composed of loss event, offspring event, and the coalescence event. And as you see here, at the t infinite limit, long time limit, there's a threshold where whether it dies out to 0 or suddenly some density becomes finite, and that's the percolation threshold. But I want to stress here that, although this is a non-equilibrium system, you can write down a free energy functional by writing a or some generating function like this and doing derivative. So just looking for the minimum of this free energy is the same as looking for the transition point. So in that sense, the Landau theory still works. Of course, this is not the end of the story, where there are also some diffusion events where the water can spread out, and also, or perhaps more crucially, because of the randomness, you'll have some noise that turns out to break the fluctuation-dissipation theorem. And this is the defining, because of these noise and the diffusion, it turns out that the dynamical exponent of this critical point is have a critical exponent that does not occur in equilibrium. But what I want to stress there is that because the transition, existence of the transition itself can be understood for the Landau free energy, the equilibrium counterpart still exists, meaning that if you change the rules such that the noise, if you could change the system such that you can tune the noise, you can continuously tune the noise that is non-equilibrium to an equilibrium noise that does obey the fluctuation-dissipation theorem. So in this sense, you can tune your directed percolation threshold, which is the non-equilibrium phase transition, to equilibrium one continuously.
Ryo, excuse me, we have a question from Juzar. Juzar, please, go ahead.
Thanks. So just a quick question. In the equilibrium scenario, once you have the free energy, you can calculate whatever you like because it's related to the partition function. Does that same logic hold true even in the case of non-equilibrium?
So,
most likely not, but I'm not sure.
So I think the short answer is no. And so this free energy itself is not the real free energy, like in the equilibrium where you cannot write down partition function and write down the Gibbs free energy or anything. But what I'm saying here is that if you ignore the noise, the mean field description can be written with some generating function. So if you don't like the language of free energy, you can think of this as a generating functional that generates this phase transition. And this if you can write down the generating functional and look for the minimum of this, at least in the mean field level, you can predict the existence of the phase transition. Of course, that scenario can change because of the noise, because that's what make it different from the equilibrium phase transitions. But what I'm stressing here is sorry.
Yeah, sorry, just to clarify. So when you say a phase transition, you're specifically referring to the fact that rho has certain properties, right? But not all, not everything else, not all possible observables, but you're specifically focusing on rho.
Right, right. I mean, but yeah,
And
you're
hence you
right.
calculate the sort of generating function for that particular quantity
Right,
that you're interested in, and
right,
not
and
like in
right,
the
right,
equilibrium case where you calculate it for everything. I mean, because free
right.
energy
But
normally would
yeah,
mean all observables would follow
right.
that.
But I'm stressing. I mean, what I'm stressing here is that rho here is the order parameter.
Mhm.
So and so this is change from 0 to finite is the just like in Ising model where phi equals to 0 changes to finite. Um, so how do I say? So I'm writing down meanfield description, which is the dynamics for the order parameter. Is that answering your question? Like,
Yeah. So I mean, just a quick follow up. So in this probably example, it's a bit simplistic, but in general, where you don't know what is the quantity undergoing phase transition, there could be several other quantities which don't undergo phase transition in a non-equilibrium scenario, but maybe one specific quantity undergoes a phase transition. Can that happen?
Can you say it one more time? Like,
So in a non-equilibrium scenario, in a more complicated setup, you could have different observables. And let's say one observable undergoes some sort of a phase transition, whereas the other observables do not undergo such a phase transition. Can such a scenario arise? And so you would calculate the generating function corresponding to that particular observable that undergoes a phase transition.
Okay, I'm not sure. Okay, so maybe it's safer to say that this is only for the order parameter dynamics and I'm assuming that we know what the order is. And so for the more general cases where it's hidden or anything, I don't have a good answer to that, maybe.
Okay, thank you.
Okay.
We have two further raised hands. So let me first, Dario.
Hello. Yeah. Sorry. Very quick question. When you say time derivative, the time is the, let's say, the label of the layer, or
right. Yes. Sorry
okay.
for not. Yeah. Right.
Okay.
Yeah.
That's it.
Okay.
And we have a question from Meng.
Yes, about this gamma dice and gamma offspring, how you define it? Yeah.
I would say this is that's a good question. I mean, this is a phenomenological description. So I'm coarse grain. I'm assuming that I could be successfully coarse grain this dynamics, which is a microscopic event to the to this meanfield description, and the way this microscopic P, I mean the way you coarse grain it is going to be probably very non-trivial. So what I'm saying is that from the microscopics, what does the gamma death and gamma offspring would be is not a trivial yeah, it's not a trivial question, I think. But so this is you should think of this as probably as the phenomenology, but it turns out that this directed percolation exponent that you can calculate or simulate does match with the microscopic model.
Can I understand? I cannot read this gamma dice of spring or colons from your diagram. This triangle diagram or this direct percolation diagram. So I cannot read this gamma from your plot.
Oh, so are you asking what's the precise value of gamma offspring is? Is that?
Yeah, how it defined from this plot?
Okay, so what I'm saying is that that's a little bit difficult to compute. Okay. I mean, you have to do some coarse graining analysis.
I see. Thank you.
And so it's not a very trivial relation, I think. Yeah. So So I think you should think of this as phenomenology that is known to work.
Yes, we have a further comment or question from Dario.
Okay.
Yeah. Sorry. It should be very simple. Instead, when you talk about the Laplacian is a, let's say, in this figure is a derivative along the horizontal direction, or
Yeah. So this
okay.
direction.
So it doesn't follow the graph. I mean, it's not connected with any. You know, in this graph there are no horizontal connections. So it's a term that is not related to the geometry of the graph. Am I right?
Geometry of the graph. I mean, there's this diffusion where like one channel changes from, one channel, but it changes the space. So what it does as a whole is like, because of this diffusion event, you can have the spreading out. And this is I is the X that I'm writing down here.
I see.
Yeah,
I see. Okay, got it.
So the diffusion is there because of these events.
Okay, and also another quick question. I mean, it looked that in order to have the phase transition, the gamma coalescence doesn't play any role?
It does. I mean, okay, so in terms of the existence of the transition itself, you're right. But it does play a role on the saturation, which is because if there's nothing like this, then the rho will increase forever. So this is something like a saturation in laser physics.
I see.
Yeah, so this is like loss and this is like gain. And then once the gain is larger than your loss, then it would start to increase, but does it increase forever? The answer is no, because of the saturation. Right.
I see. Okay, thanks.
Yeah, thanks for the question. Right. Okay, so thanks for all the questions. So it turns out that almost all the known non-covalent phase transition, at least in the mean field level, can be understood from the Landau free energy argument, where you can include lasers, optical bistability, and which can happen in a driven optical devices, and also flocking transition of the birds. And there's something called the motility-induced phase transition that have been discussed in the active matter community, where each particles, not just that the particles are not driven only by the thermal fluctuation, but can drive itself, because when they have, each particle have their motors inside that can self-propel, it turns out that you can have this kind of phase separation can happen even in the absence of attractive interaction. And but these non-covalent phase transition can also be described in terms of free energy like this. So of course, these noise may or may not break the fluctuation-dissipation theorem. And that is why there are many phenomena that can occur that is unique to non-equilibrium. But if you ignore the noise and only look at the mean field description, the Landau free, it's going to be the same as the equilibrium, and therefore, by tuning the noise to be following the fluctuation-dissipation theorem, you can make the system to tune the system from non-equilibrium to equilibrium. So in this talk, I would like to introduce something new, which is the phase transition does not belong to this class, where you cannot have some minimization of energy anymore. And I would like to tell you what I mean by that, and we call this non-reciprocal phase transition. Okay, so this is just a recap of what I've been saying on the Landau theory, where you first write down all the terms in terms of the order parameter allowed from the symmetry, and then you look for the minimum, which is looking at the derivative of the free energy like this. And the point where the minimum changes is the phase transition point. And it is very easy to generalize the multi-component system. What you do is you only have to make the parameters, the coefficients into matrices or tensors. And again, you look for the minimum, but one very strong constraint that you'll get from this is that because you're differentiating the free energy, the coefficients have to be symmetric. Even if you by hand put these coefficients to be asymmetric, all the equation that that arise in here is going to be symmetrized. So this is a restriction that you will always get as long as you assume a free energy. However, if you're away from equilibrium, these doesn't have to be the case. So although in non-equilibrium systems, you cannot write down the free energy, what you can do is to directly write down the dynamical system or the equation motion of the order parameter. So what I'm doing here is that I'm writing down a dynamical system, and I'm writing down the right-hand side, all the terms that is allowed from symmetry. This looks very similar to the one that I showed in the previous slide, but because I'm not assuming that this is a derivative of the free energy, all the coefficient doesn't have to be symmetry. Like for example, alpha AB does not have to be equals to alpha BA. Because of that, if you, for example, look for a non-equilibrium steady state, then you'll get this equation motion. I mean, you'll get a nonlinear version of a non-Hermitian eigenvalue problem. For those of you who are familiar with the non-Hermitian physics, might think that this is quite similar to the usual linear non-Hermitian problems discussed in optics, but I would like to stress that this is a nonlinear version where the saturation occurs. And so unlike in the usual optics problem where they look usually at the response of the system or some conditional dynamics of the quantum trajectory, I'm looking here at the nonlinear non-Hermitian eigenvalue problem and looking for a steady state of the system. So yeah, so because this system is non-Hermitian, what happens is that, well, if it's a Hermitian system, these eigenvectors have to be orthogonal to each other. However, when it's non-Hermitian, it does not have to be. And there's a special point called an exceptional point that they coalesce. It turns out that this exceptional point marks a phase transition point. Depend on the symmetry, what we call PT symmetry. These exceptional point can rise as a line of the phase in the phase diagram, or as a point of the phase diagram, which is associated with the first order like phase boundary, just like a liquid gas transition in this 2-parameter space. And I would like to stress the generality of this approach. I would like to, as long as the system you're looking at is a many-body non-equilibrium system and spontaneously break the continuous symmetry, and also is composed of 2 or more components so that you can define a matrix, then this whole mechanism can arise. Because this exceptional, this singular critical point is associated with the exceptional point, it means that this is a non-diagonalizable matrix. So because this is non-diagonalizable, it means that when you should triangularize the matrix because you cannot diagonalize. And because of this form, this means that the two collective modes, phi1 and phi2, are non-reciprocally interacting. It's a one-way coupling where 1 is affecting the 2, but 2 is not affecting the 1. And this is undoubtedly breaking the fluctuation, the detail balance. If the detail balance is holding, then this cannot occur. So in a strict sense, there is no equilibrium counterpart of this type of phase transition. Okay, so let me give some concrete example to give you what I'm more flavor of what I'm talking about. So what we first look at, and in fact, this is the first system that we found this type of phase transition, is the external pluridon condensate. So for those of you who don't know what the pluridon condensate is, I'll show you what the system. So external pluridon system can arise in a semiconductor embedded in a cavity. So if you pump a light on a semiconductor material, electron and holes can arise. And because of the equivalent interaction, they form a bound state called extons. And then because, of course, the extons will not live forever because it's an excited state, and it will, after a while, it will pair annihilate and become a photon again. But because of these Bragg mirror, the photons are captured here. And because of this, the electron, within this semiconductor system, you'll get an electron hole photon many body correlated system to arise. Of course, if that's the story, you'll get an equilibrium many body system, but because the mirror is always not perfect, you'll have a leakage of photons. So this means that in order to have a steady state, you should have a continuous pumping of light in order to get a steady state. So now this system does satisfy the three conditions that I just talked about. Namely, it's non-equilibrium because this is a driven dissipative system. It's because it forms a BEC. This is a spontaneous symmetry broken system. And also, the system is composed of photons and extons, so it also satisfies the condition that I just posed. So let me be more precise. So because the microcavity captures photon, you'll get one dispersion like this, which is the photon dispersion. And this is coupled to the extons, but this cavity is tuned such that the extons and photons are at least close to the resonance. And because this is designed such that the system, extons and photons strongly couple, it forms a hybrid mode called polaritons, and which is divided into two modes, the lower polariton and the upper polariton, which corresponds to like in-phase motion of the extron and photon versus the out of phase, which corresponds to the upper polariton mode. And once you have many particles inside, you can form a BEC here. Actually, the observation of the polariton BEC have been done like 15 years ago by now, and 1 year later, even the room temperature BEC could be done. So, but again, because this is a driven dissipative system, this is a non-equilibrium Bose-Einstein condensate. And so what was puzzling about the system was that it turns out that if you pump the system strongly, namely that if you tune the system density to be larger and larger, you'll see another threshold or another phase transition. So here's the data, which is observed, in fact, in many groups that I've listed here. So this x-axis is the photon pumping power, which increases the photon and exon number. And this y-axis is the intensity at momentum 0. So some increase of this intensity means that there's a Bose-Einstein condensate occurring. And this energy is the emission energy of the k equals 0, which is the condensate emission energy we want. So as you see here, there's a clear first threshold that happens, which signals that there's a condensate appearing, but there's another one. I think it's clear from this intensity, but it is also clear from more clearer from the emission energy here, where the emission energy is clearly jumping. So people have been thinking that this is a signature of the pluridon BEC to the photon laser transition. What I mean by that is that when the pumping power is so large, this system, because the system itself is a semiconductor embedded in a cavity, which is namely very similar to the semiconductor laser system, it is known that at very, very high pump power, it does behave just like a photon laser. So it was interesting how the BEC and the laser, photon laser, can happen at the same time. But the question is, why is there a transition in between these two? And for a theorist, this is pretty puzzling, because if the reason for the transition was that there's a transition from normal to photon laser, well, the photon laser have a threshold because there's the normal phase turn into a coherent phase, or namely there's a spontaneous symmetry breaking occurring from the normal to photon laser state. But the pluridon BEC is already in the U1 broken phase. So there's no new broken symmetry. So why is there a transition? It's something that we have to give a theory about. And we would like to argue that our answer is that this is a non-reciprocal phase transition. So let me give the flavor of what we've done. I mean, what we are arguing. So as I said before, because it's a hybrid system of upper and lower pluridon, and of course, the Bose-Einstein condensate would usually occur in the lower branch because that's a lower energy. But remember that this system is non-equilibrium. So there's no reason to say that upper pluridon condensate cannot occur. And indeed, we've shown that it can occur. And our interpretation is that this system can exhibit the lower branch to upper branch condensate transition. And in fact, we have done a very serious calculation on the using Keldysh theory from the microscopic electron hole photon system, and could write some qualitative phase diagram of this, and could show that in fact, this lower branch condensate and upper pluridon condensate, if you tune the system, there's a point that they coalesce as the exceptional point. And because of that, we're saying that the phase diagram will look like this, where an exceptional point marks the phase boundary, first order like phase boundary of the system. And so the x-axis is the pump power, the y-axis is the photon decay rate. And if you sweep the pump power as done in experiments, you'll see two thresholds from the normal to superfluid and superfluid to another upper branch condensate. So, so to give you a little bit of how we did that, I mean, of course, what we did is we started from a very microscopic theory and write down the exact equation motion of that microscopics, but I don't think that would be helpful to give you all the details of that. But I can tell you that this can occur from the minimum model, namely from the GP equation. So for a one component superfluid in equilibrium, at the mean field level, the Gauss-Pitoevsky equation or the GP equation works fine, which is namely the nonlinear type of the Schrodinger equation, where the nonlinear arises from the repulsive interaction. When there's two components, which is photons and extons, this will start to look like this, which is a two components coupled GP equation. And when there's drive and dissipation, where the photon, I've incorporated the photon loss and the gain of the exton, pumping of the extons, as well as the saturation effect that is there, you'll get this 2x2 matrix, non-Hermitian, nonlinear equation motion. And when I assume that this would approach a uniform steady state like this, you'll get the nonlinear, non-Hermitian eigenvalue problem. And if I I compute this, where I'm plotting the emission energy versus the pump power versus the decay rate, we find that there is a phase discontinuous jump here that ends at the exceptional point as promised. So this is the our scenario of having why there's a discontinuous phase transition. So
Ryo, excuse me, we have a question from Ming.
Okay.
Yes, thank you. Could you explain what is this parameter G? I think here this psi L and psi G is the
G is here,
lower and upper branch of the exon polariton. But what is the coupling between this lower and the upper branch?
Sorry, so this is L is the loss component, which is photon, and this
okay.
G is the exon,
okay,
and
I see.
small g is the Rabi coupling.
Yeah. Okay, so basically it's the basic exon polariton physics. Okay, thank you very much.
Right. But I'm putting in some nonlinearity and the pumping and decay.
Yeah, yes, right.
Yeah, and it turns out that there is a point that where this discontinuous jump will coalesce and stop, which looks like a endpoint of a liquid gas transition.
Thank you very much.
Right. So because this is a critical point, and because this looks so much like a liquid gas transition, one might ask, is there a critical phenomena at this exceptional point? It turns out that the answer is yes, but from a very fundamentally different mechanism from the usual critical point. So in the usual conventional critical phenomena, for example, I'm writing down a U1 symmetric system from the superfluid, the ordered phase to a disordered phase transition. You usually get one, okay, in this system, you'll have Ghostan mode, and there's another amplitude mode. And as you approach the critical point, the amplitude mode softens and become gapless, and this is occurring due to the flattening of the free energy landscape. But it turns out that at our exceptional point, or it's probably fair to call it a critical exceptional point, unlike in this system where the free energy is flattening, the Ghostan mode and the other damping mode, because it's a driven dissipative system, the mode does not have to be orthogonal to each other anymore. And at the exceptional point that I showed you, these two modes coalesce. And because of this, it turns out that the fluctuation becomes very giant. Giant in the sense that it diverges at a 4-dimensional less, at least in the Gaussian level, which is to be compared to the usual case where the Mamring-Wagner theorem tells you that this divergence occurs at 2-dimensional less. And after from the dynamical RG that we performed, it turns out that the upper critical dimension, or the dimension that the many body effect become relevant, goes all the way up to 8 which is to be compared to the usual Ising model where you get the critical dimension is 4. So this is clearly a new universality class. So I don't want to go into much detail about this, the technical part, but what you can do is that starting from the open quantum many-body system equation motion, there's a way of coarse-graining the system, and it turns out that although this system is a quantum many-body system, it turns out that by coarse-graining the system, you can safely analyze this critical behavior from just a semi-classical noisy equation motion where eta here is a white noise. So this has been known for a one-component system, and we simply use this analysis and generalize it to a two-component system. And so further integrating out the amplitude fluctuation and so that we can get a phase-only equation motion, what we end up getting is a coupled KPZ type equation of motion like this. So let me start with a linearized theory, meaning that all the nonlinear terms that can arise from in the phase mode is ignored. In this case, if you look at the collective mode, look like this, where small gamma is a parameter that parameterizes the distance from the exceptional point, where gamma equals 0 is the exceptional point. So when it's away from the exceptional point, this have two mode, where one is a gapless, which turns out to be a diffusive mode because of the driven dissipative nature, but the other one is gapped. And as you further coarse grain the system by doing RG, this gap mode does not play any role. So this just go back to the one component system. So, so if you're away from the exceptional point, this the two component nature does not matter at all. And it turns out it is known that this driven dissipative superfluid system follows the KPZ scale. So at the exceptional point, however, these two modes become both gapless, and namely interesting, become a sound mode again, meaning that both modes contribute to the low energy physics and the scaling law is more modified. So, right, so one mode is, of course, the Goldstone mode, which is the in-phase motion that's coming from the global symmetry. But there's another mode that is a damping mode, which turns out to coalesce, becomes the same thing as the Goldstone mode at the exceptional point. And because I'm running out of time, I'm going to skip some of the details. Sorry about that. But it turns out by looking at the propagators of the system, the fluctuation becomes very large, meaning that the phase fluctuations becomes as large, giant, and diverges at 4-dimensional less. So probably, maybe this slide is perhaps more useful to understand intuitively why anomalous giant fluctuations happen at the exceptional point. So let me just, first, very simplicity, just consider this equation motion that is linear, unlike in our system, which is nonlinear. And just consider a system which have two systems and compare, where both have the same common eigenvalue, so common damping rate, but with a different off-diagonal. And this is already triangulized, so meaning that having a large off-diagonal means that it is more non-orthogonal. So if you compare this, these two dynamics with some initial condition, it turns out that this eigenvector, in the case where the eigenvectors are close to orthogonal, it just damps and that's it. But in the non-orthogonal case, there's a amplification of the perturbation. So where does this come from is as follows. So if you have two mode that that is one is slow and one is fast, and let's say there it was orthogonal, then if it were orthogonal and you perturb the system from the fixed point to this position A, what would happen is that it will just damp. I mean, the fast mode will damp fast, and then the amount of fluctuation is dominated by what I mean the slow eigenvector. I mean the slow mode. But here, because the two eigenvectors are non-orthogonal, what happens is that the trajectory of this damping, I mean, when the system is perturbed to this position A, it first go around like this through B and then go back. So there's this amplification that happens due to the non-orthogonality. But I want to note that our case is the extreme case of this, where, of course, it is an exceptional point. So it's not only that there's very non-orthogonal, but it's coalescing, but also the damping rates are zero because this is a critical point. And so because of the Goldstone mode, these are the fluctuation enhanced by infinity, and that's where the two extra dimensions show up in the lower critical point. And I think I'll skip this part, but we did some dynamical renormalization group analysis to this, and turns out that the upper critical dimension becomes anomalously large, which is going up to 8, and due to some emergence of some dangerously irrelevant terms, but I'm not going into details about this. But the punchline is that we have some new universality class that does not occur in the equivalent phase transitions, nor the usual non-equivalent phase transitions. So, okay, so I think I have 5 minutes left.
Yes.
Okay, so I'll try going through the active matter system that we analyzed. So, so up to here, we were looking at the quantum many-body system, but the quantumness is not essential, is what we noticed, and that's how we started talking to the Professor Vincenzo Vitali and Michel Fruhert, who is an expert in active matter system, which is a classical system, but is driven out of equilibrium. And so active matter system is where each agents are living. And usually if you're dealing with dead particles, they are reciprocally interacting. But if you're looking around the world, you'll immediately notice that that's not always true. So if you look at the poor pigeon that is chased by a falcon, this is clearly a non-reciprocal interaction. Pigeon is running away and falcon is chasing. So this is the interaction between the pigeon and falcons are non-reciprocal. And these kind of non-reciprocally interacting systems are ubiquitous in nature. Not only the prey and predators, but the neurons that compose your brain are composed of inhibitory and exhibitory neurons that are known to be non-reciprocally interacting. And there's also some complex plasma or reactive optic matter systems that you can design. I mean, you can tune the interaction to be non-reciprocal in the lab too. And what I'm particularly interested in is what would happen when these non-reciprocally interacting agents are brought with many agents, and what are the collective properties of that. So to give you a flavor of what would happen, let me give an example of non-reciprocal friendship, which is unfortunately what does happen in your life probably. So let's say you have there's two person A and B, Alice and Bob, and let's just denote the distance between those two as how close their relationship is. If they like each other, which is a real reciprocal relationship, well, that's idealistic. They can be best buddies and that's it. And when there's reciprocal but repulsive interaction between those, when they dislike each other, of course, that's not an idealistic case, but in a sense, it's not a problem because we can just run away from each other and never talk to each other and both are happy. But if they're non-reciprocal, that's the most complicated things start to happen. And because there's no configuration that makes both of them happy, there will be some frustrations. So because non-reciprocal interaction generically give rise to some frustrations. So what does it do? It does induce dynamics. So this is the similar setup where child A and child B are non-reciprocally interacting. So A likes B, and okay, so the setup is that you have a table, there's a bunch of chairs, and the child have to decide where to sit. And when A likes B, A wants to sit next to B, so that's what A will do. They get closer to B, but B hates A, so he run away, and so A chases B and B chases. So this kind of chase and runaway motion start to be generated, and this because A and B are never ever satisfied, the chase and runaway motion intrinsically generates, and so this rotating mode will never occur if they're not interacting. So okay, so to make this into some simple math, I can consider this as this angle as a continuous value. So this is some kind of a non-reciprocal version of the XY model, if you want. So it turns out that this interacting dynamics that occurs is not going to be occurring as a steady state. It's only there in the transient dynamics. So this XY model, if you try to write down the equation of motion, it turns out that there's only two fixed points, 0 or pi. And so it's either that A and B are sitting next to each other or being furthest are the two fixed points. And this is intuitively very simply understood because A chases B, but whenever A is better than B at chasing, then A catches B. And that is the end of the story. And the opposite is true. When B is better at running away from A, then they just, B is going to get happy with the pi shift. And because B is better than A at chasing or running away, they will just sit there. So in the long time limit, the dynamics will die out in a two-particle case. But what happens in the non-many body case is the question. So let's consider some interacting. This is called a Vic-Check model, but the detail doesn't really matter. This is something like an XY model where each agent see their neighbors and okay, sorry. So blue is within the group A, red is within the group B, and A wants to be aligned with A, B wants to be aligned with B, but A and B are non-reciprocally interacting, meaning that A wants to align with B, but B doesn't want to. So this is the model that we simulated. And here's what's going to happen. So in addition to the disordered and this usual flocking phase where A and B align, there's also some anti-align system where A and B are propagating, traveling in the opposite way. But there's another mode, the interesting one, where the oscillation occurs. And as you see, the oscillation would occur even in a long time limit. So this is some kind of frustration-induced time-dependent phase. And it's associated with a spontaneous Z2 symmetry breaking. So how do we understand this is as the following. Sorry, I'm running out of time, but let me just try to finish. So as I said, when there's no noise but two agents, it will go to a fixed point and it's not gonna move. But if you add noise to this, there's this noise will perturb the state. And then because of that, the chase and runaway search again resorts. But of course, this noise is so random that there's no order in this system. But because there are many, many agents A that tries to align with each other, the many-body interaction make this into a rigid state. And that is why they will stabilize the collective motion and that therefore stabilize this correlation. So this chiral phase is coming from the combination of the non-reciprocity induced frustration plus the many-body interaction plus the noise. And I think this is quite similar to the order by disorder transition known in frustrated systems, because this is like in the frustrated system where the noise induced some order. This noise, I mean, in this system too, the frustration is giving rise to some interesting phenomena where the noise is activating some ordered system. Right. So, yeah. So what we can do is write down coarse grain the system and write down the hydrodynamics of this. And I'm not going to the details about this, but the align to the chiral phase transition that I showed you is marked by the exceptional points that I've been talking about. Okay, right. And at last, I'll just mention that, in fact, this chiral phase is not the only phase that only time-dependent phase that we saw. In addition to this chiral phase where the angles are rotating, there's also what we call the swap phase where the amplitude are starting to chase each other. And there's also some quasi-periodic phase, so where the chiral, the angle and the amplitude is both chasing each other like this. And as it turns out, these two phase and amplitude motion combined will give rise to a quasi-periodic many-body state. So I think with that, I'll just stop and try to summarize, where we introduce a novel type of phase transition that we call non-reciprocal phase transition, which strictly has a non-equilibrium counterpart because it's marked by a spectral singularity called the exceptional point. And these are associated with time crystals, and I didn't have time to go through, but it's also, depending on the symmetry, it can have hysteresis and anomalous critical phenomena and so on. And it's, I want to stress that this is a very generic mechanism that we found, that the only ingredient you need is a driven dissipated or breakdown of the detail balance, and continuous symmetry breaking and having more than two components. And thank you very much.
Thank you, Ryo, for your excellent talk. Let us thank our speaker. And we have time for questions. Yes, Juzar, please go ahead.
Maybe a silly question. And just coming back to your last example of flocking, why are these sort of birds, if I call them, why are they not just, forming two groups at two corners of your simulation box? Why
sorry. So there is not, yes, thank you for the question. But so this is not the like repulsive or attractive interaction. They're not chasing one to the other. They're just aligning or anti-aligning. So there's,
I see.
So there's no reason it just phase separate.
I see. So what you mean by the ones from the same group, they just like to align with each other, and that's
right.
It.
Right.
I see. Okay, thank you.
Okay, Sergey has a question. Please, Sergey.
Yeah, one question is, So you stress this difference between the non-equilibrium or non-reciprocal phase transitions and systems and the reciprocal ones, or let's say the equilibrium phase transitions. Still, there are parameters, right, which tell you how far you are away from equilibrium. What happens if I try to tune these parameters back to, so to say, 0 or to the equilibrium values? What will happen with these new or with these non-equilibrium phase transitions, the particular ones which you discussed here?
So it's gonna disappear is what we are stressing.
What means disappear through what
like
kind of mechanism?
Okay, so right. So for example, maybe let's see. Maybe just showing the phase diagram. Sorry. Yeah, here. So this is the x-axis and y-axis is the, okay. So JAB minus JBA is characterizing how large the non-reciprocity is. And J plus is the sum of JAB and JBA. And so, this line, I mean, if you draw a horizontal line, which is J plus equals to J minus, is a line where the JAB and JBA becomes the opposite sign. So this region, sorry, I'll just annotate. I'll try annotating. Hope I can. Where's the, sorry, I can't. Sorry, let me.
Okay, maybe you don't.
Yeah, sorry. I asked for you. Yeah, so or maybe yeah, for some reason I can't see clearly what's happening. But okay, but sorry. So in this region where the sorry, so J minus equals to 0 is the reciprocal limit. And in that case, there's only aligned and anti-aligned. And yeah, actually this point at J minus equals 0 is a singular point and there's no exceptional point here. I think it's going to be a Dirac point, I believe. Yeah, and so there will be no chiral phase occurring and therefore no exceptional point will arise in this system.
Okay, so back to your phase transition. So what you showed, is that in these new phases which emerge due to, say, the existence of two components, no, which you definitely need at least, is a new state which I think you called it chiral in some case, but essentially it looks to me like some generalized limit cycle. Could we call it that way? Right.
Yeah, I think so.
Now,
yes.
there are similar mechanisms by which you can. So I think I could now try to make the discussion much simpler and remove all the extensions in real space, meaning that you have fields which vary not only in time but also, or components, but also in space. And if I, so to say, forget about all the space dependence, then I would consider some kind of system of two coupled degrees of freedom, right. And then if I could again probably look at non-reciprocal situations, but I could just in general look at some nonlinear dynamic solutions in such a dissipative system, and I would find in general that it can have fixed points, and then there can be bifurcations, and these fixed points can bifurcate into other fixed points, or what can happen is that they can suddenly all become unstable, and the only stable attractors which will survive are, let's say, limit cycles, or even more complicated objects. As we know, there are strange attractors, chaotic attractors, and God knows what, which one can come up with. How are these things related to this non-reciprocal phase transition ideas we discussed
yeah,
here?
in fact, actually, we are preparing a paper on that. I mean, in fact, I don't want to spoil anything because it's a work that's ongoing work with my collaborators. But yeah, it's actually we are starting to notice that, as you said, the language that we should use is this dynamical system language, which is like limit cycle and so on. And yeah, so two limit cycles. Yeah, so I can call it this way. So two limit cycles. Okay, so in the aligned state, let's see. So in the chiral phase, there are two limit cycles, right? Because there's one limit cycle and there's another limit cycle. And then, yeah, so they coalesce at the exceptional point. And so we can sort of say it in that kind of language. And
I mean, to my understanding, this is still much more than saying, oh, it's the same as in this nonlinear dynamics, in this low dimensional few degree of freedom systems. But there are lots of similarities. Of course, you have this notion that you embed this into infinitely many degrees of freedom because you have spatially varying fields as well, in addition to time variation.
So in terms of the dynamical system language, the closest that we know is what's called the Bogdanov-Tuckins point, which is the point where, so if you have like 2 degrees of freedom, like a 2 real system, and then so you can have 2 fixed points, but also some limit cycle as well. And there's a point called the Bogdanov-Tuckins point where, okay, so depending on the parameter, the Bogdanov-Tuckins point, so you can have a half bifurcation, but in the other side, you can have a limit cycle. And there's a point that the half bifurcation turns into a limit cycle and turns into a half bifurcation. So half bifurcation and sorry, did I say the same thing? I mean, sorry, the pitchfork. Sorry, I think the pitchfork bifurcation. Sorry. Wait, I have to be careful. Not the pitchfork. But anyway, sorry. So some fixed point is bifurcation, and the limit cycle bifurcation kind of occurs at the same point as the what's called the Bogdanov-Tuckins point. And that do have a very similar system where the eigenvectors call that. So
right. Perhaps my question currently can be boiled down to the following. I mean, if you now go back into this low dimensional few degree of freedom, well-known studies which have been done to quite some extent, is there any notion also of this non-reciprocity in these low dimensional systems, which is giving rise to some new bifurcations similar to what you discuss here in these many-body interacting principal systems? Or is there something indeed new which is brought into the game by the fact that you have a many-body system?
Okay, so as you said, if I ignore all the noise and ignore all the nabla terms, which is what we did here, yes, this is no extension of the dynamical system. So I think it is fair to put this, I mean, as far as we know, we did not see any dynamical system literature that look at this kind of critical exceptional point. But you're right, I think it should be along the line of those. And but as you said, I mean, when you put in the many-body interaction and the noise and the spatial degrees of freedom, of course, one thing that starts to occur is the critical phenomena, which I showed. And actually, also, there's one example where the spatial degrees of freedom does matter, which is that so in the flocking model, there's some convective term. I mean, okay, unlike the usual XY model, the order parameter is velocity. So because of that, there's like not only the round TV, but there's like round TV plus v dot nabla v term that appears in the dynamics. And because of this, it turns out that this at the exceptional point, this system is necessarily unstable against the phase fluctuations. So because of that, okay, I hope it's restarting. Okay. I don't know how to restart, but anyways, yeah. So there's this pattern formation occurring where a bunch of vortices spontaneously arise, and these physics of this pattern formation physics is something that you cannot have without the spatial divisible freedom. So yeah, so right. So as you said, mean field level with no nebula and no noise is some extension of the dynamical system literature, but we believe that there's more to that.
Thank you. Thank you.
Yeah.
We have questions or comments from Alexei also. Please, Alexei.
Yeah, actually a very simple one. So how far, I mean, when talking about dynamical frustration or frustration generated dynamically, you also mentioned the order by disorder connection. So how far can you push this analogy?
In
That's
fact,
one
we
question.
don't. Yeah.
Yeah, and the second question is, would anything change if, say, in the last model that you considered, the Bishik model, I believe, what would be the effect of disorder? So if not only you allow couplings to be non-reciprocal, but you also make them different for different agents.
And that is an excellent question, and in fact, that's exactly what I'm investigating right now. So yes, that is an interesting question that I really want to know the answer to. Right, but so far we have no idea how far we can push this analysis. I mean, an analogy. Sorry. Yeah. So we are very interested in that question. Thank you.
Okay. Thanks.
Okay, maybe let me have a quick question also. Coming back to the exciton-polariton experiments that you were showing. So you've shown the two transitions, right? And the second one is this new one that you identified. Did they, in the experiment, also see the exceptional point? Are they able to go to that regime?
So, okay, so actually, sorry. Wait, but for some reason I'm failing to. Okay, here you go. So, yeah. So, right. So, we did some microscopic analysis, and we can kind of guess where the photon laser and the I mean, we can kind of guess what the phase diagram looks like. So here it is. So this delta is, you see here, is what's called the detuning parameter, meaning that what's the energy difference between the photon energy and the exciton energy. And you can tune that experimentally. And as you see here, well, I mean, I'm not going to the details about this, but the exceptional point would arise only in the delta being positive. It's called the blue detuning regime. While in the red to zero detuning, we could kind of qualitatively predict from some discussion on how the parameters would flow that the phase diagram looks like this. So in this case, you always see if the kappa is small enough, which is indeed the case in experiments, you will always see a phase transition, second threshold. But in the blue detuning, you don't. It depends on the detail. And experiments have seen a second threshold in these regimes. And in the extreme blue detuning, they saw no threshold. And so somewhere in the between, there should be some exceptional point. And that's an ongoing work that is done in the Michigan University, and but we're waiting for how it goes.
So there you expect, you said large fluctuations, right? So kind of, simply speaking, everything should blow up, or what?
Yeah,
kind of.
like yeah. So maybe, I mean, so what we've done in the RG analysis is only the 8 minus epsilon expansion, which I'm not sure how useful it is. But it's only valid at spatial dimension 8 or close to that. But so we frankly don't know what will really happen in 2D. Like maybe some phase defect would occur. But yeah, but at least what we can, yeah. But the phase fluctuation should diverge there. So yeah, what we think is going to happen is that like many vortex anti-vortex pairs would arise there, and the phase correlator at least can be measured experimentally. So that will be something to look for, and also actually, yeah, perhaps more simpler thing to look for is the fact that so the fact that the propagating mode would occur. And I mean, so usually you only have a dissipative mode, a diffusive mode, but at the exceptional point, note that because it's the exceptional point, there's some square root behavior that shows up. And because this is square root, although all the spatial differentiation is only there's only k squared, this turns to a sound mode. And because of this, the propagating modes start to appear, and that might be some signal that experiment can see. We are hoping.
Okay, thank you. Are there any further questions from the audience? In case not, let us thank our speaker again.
Thank you.
So with this, we conclude